Hello, everyone, and welcome. Today we're diving into a new core topic. Chapter 8, Probability Distributions. This is a fundamental area of statistics that helps us understand and predict the world around us, from the outcome of a simple coin toss to more complex phenomena. By the end of this chapter, you will be able to understand what discrete random variables and their probability distributions are. You'll also be able to calculate and interpret the expected value of these variables, and importantly, apply these concepts to real-life situations. The core idea here is that probability allows us to quantify the likelihood of events. It gives us a framework for making predictions and informed decisions, even when dealing with events that seem random. We'll be focusing on how we can model these situations and find structure in what appears to be randomness. This is the key to bridging the gap between theoretical probability and what we observe in reality. Take a look at these images. We see the world's tallest man and shortest man, a high jumper at the peak of their jump, and one of the world's oldest people. Each of these represents a variable, like height, athletic ability, or lifespan. Are most people's heights clustered around an average, or are they spread out evenly? Probability distributions help us answer exactly these kinds of questions. Before we jump into new material, let's warm up with a couple of problems that rely on your prior knowledge of basic probability and data representation. This will ensure we have a solid foundation to build upon. First, consider this problem. A bag contains 6 red and 4 blue balls. In total, that's 10 balls. We're going to remove 2 balls at random without replacement. We need to find the probability of getting 2 red balls and the probability of getting exactly 1 red ball. Let's tackle part A. The probability of the first ball being red is 6 out of 10. Since we don't replace the first ball, for the second draw there are only 9 balls left, and only 5 of them are red. So the probability of the second ball being red, given the first was red, is 5 out of 9. We multiply these probabilities together. 6/10 times 5/9 is 30 over 90, which simplifies to 1/3. So the probability of drawing 2 red balls is 1/3. Now for part B, getting exactly 1 red ball. This can happen in 2 ways. We could draw a red then a blue or a blue then a red. We need to calculate the probability for both scenarios and add them up. The probability of red then blue is 6 over 10 times 4 over 9. The probability of blue then red is 4 over 10 times 6 over 9. Notice the denominators decrease to 9 because of no replacement. Both scenarios give us a probability of 24 over 90. Adding them together, we get 48 over 90, which simplifies to 8 over 15. So there's an 8 in 15 chance of drawing exactly 1 red ball. Great. Now for the second review problem. We need to draw a box and whisker diagram for the data set 2, 6, 8, 9, 10, 12. This diagram is a great way to visualize the spread and center of a data set. First, we need the 5-number summary: the minimum, first quartile, median, third quartile, and maximum. The data is already in order. The minimum is 2 and the maximum is 12. These will be the ends of our whiskers. The median or second quartile is the middle value. Since we have an even number of data points, it's the average of the 2 middle values, 8 and 9. So our median is 8.5. The first quartile, Q1, is the median of the lower half of the data, which is 6. The third quartile, Q3, is the median of the upper half, which is 10. Now we can draw the plot. We draw a box from Q1 to Q3, so from 6 to 10. We draw a line inside the box at the median, 8.5. Finally, we draw the whiskers out to the minimum value of 2 and the maximum value of 12. This plot gives us a clear visual summary of our data. All right, with that review out of the way, let's introduce our first key concept for this chapter. We're going to be talking about discrete random variables. So, what is a discrete random variable? It's a variable whose value is a numerical outcome of a random phenomenon. The discrete part means it can only take on a finite or countable number of distinct values. We usually denote these with a capital letter, like X. For example, if we roll a standard 6-sided die, the score we get is a discrete random variable. It can only be 1, 2, 3, 4, 5, or 6. We can then talk about the probability of this variable taking on a specific value. For instance, we can write a statement like px equal 2 is a 1/6. This simply means the probability that the score on the die is 2 is 1/6. This notation is central to our work in this chapter. When we list all possible values of a random variable, along with their corresponding probabilities, we create what's called a probability distribution. A probability distribution gives us the complete picture of the probabilities for a random variable. It tells us everything we can know about the likelihood of its possible outcomes. This is often displayed in a table for clarity, which we'll see in our first worked example. Let's apply these ideas to a concrete example. This is worked example 8.1 from your textbook. The problem states, a drawer has 5 black socks and 3 red socks for a total of 8 socks. We draw 2 socks without replacement. Our goal is to find the probability distribution of the random variable x, where x represents the number of red socks drawn. A tree diagram is an excellent tool for visualizing the possibilities and calculating the probabilities here. For our first draw, there are 8 socks in total. The probability of drawing a black sock is 5 out of 8. The probability of drawing a red sock is 3 out of 8. Now let's consider the second draw. Remember, it's without replacement, so there are only 7 socks left. If our first draw was black, there are now 4 black and 3 red socks left. So the probability of the second being black is 4/7, and red is 3/7. If our first draw was red, there are 5 black and 2 red socks left. So the probability of the second being black is 5/7, and red is 2/7. Now we can calculate the probability of each complete path or outcome. The probability of drawing 2 black socks, BB, is 5/8 times 4/7, which is 2056. For black then red BR, it's 1556. For red then black RB, it's also 1556. And for 2 red socks, RR, it's 3/8 times 2/7, which is 656. Our random variable x is the number of red socks. Let's find the probability for each possible value of x. X can be 0, 1, or 2. X equals 0 corresponds to the outcome BB, so Px equals 0 is 2056, which simplifies to 5/14. X equals 2 corresponds to the outcome RR, so Px equals 2 is 656 or 328. X equals 1 corresponds to 2 outcomes, drawing a black then a red or a red then a black. We need to add their probabilities. So P of x equals 1 is 1556 plus 1556, which equals 30 of 56 or 15/28. Now we can present our final answer as a probability distribution table. Here's the table. It clearly shows each possible value for the number of red socks x and the probability of that value occurring, Px equal x. This leads us to a very important property of any discrete probability distribution. The sum of the probabilities of all possible outcomes must always equal 1. This is a fundamental rule. It means that one of the possible outcomes must occur. Let's check our work. We need a common denominator, which is 28. So 5/14 becomes 10/28. Adding our probabilities, we get 10/28 plus 15/28 plus 3/28, which equals 28/28. And that is indeed 1. Our distribution is correct. Let's move on to another example, worked example 8.2. This one will test our understanding of the key property we just learned. We are given the probability distribution for y, the number of cracks observed in a 1-kilometer region of a sewer pipe. Notice that one of the probabilities is an unknown value, k. We have 3 tasks. Find the value of k, find the probability that y is less than or equal to 1, and find a conditional probability. First, let's find k. How do we approach this? We use the key point from the last scene. The sum of all probabilities in a distribution must be 1. So we set up the equation, 0.45 plus 0.3 plus 0.15 plus k must equal 1. The known probabilities sum to 0.9, therefore k must be 1 minus 0.9, which is 0.1. Now for the second part, we need to find the probability that y is less than or equal to 1. This means y can be either 0 or 1. To find this probability, we simply add the probabilities of these two outcomes. P equals 0 is 0.45, and Py equals 1 is 0.3. Adding them together gives us 0.75. So there is a 75% chance of finding 1 or fewer cracks. Finally, let's tackle the conditional probability. This question asks for the probability that y equals 0, given that we know y is less than or equal to 1. The vertical bar means given. The formula for conditional probability is P of A given B equals P of A and B divided by PB. In our case, A is y equals 0, and B is y if 1. So we need to find the probability of y being 0 and less than or equal to 1, and divide that by the probability of y being less than or equal to 1. Think about the numerator. If y is 0, it is automatically less than or equal to 1. So the event y equals 0 and y1 is just the same as the event y equals 0. So our calculation becomes p of y equals 0 divided by p of y to 1. We already found p of y to 1 in part B, so we have 0.45 divided by 0.75, which equals 0.6. This means if we know there's at most one crack, there's a 60% chance that there are actually 0 cracks. Now that we're comfortable with probability distributions, let's introduce another crucial concept: the expected value. What do we mean by the expected value of a random variable? Imagine rolling a fair six-sided die over and over again, thousands of times, and calculating the average of all your rolls. What number would you expect that average to be close to? It wouldn't be a whole number. The average of the possible outcomes is 3.5. This value, 3.5, is the theoretical mean, or the expected value of a single roll. It's important to note that the expected value is not necessarily a possible outcome. You can't roll a 3.5. It's also not necessarily the most likely outcome, which is called the mode. The expected value, which we denote as e of x or with the Greek letter mu, represents the long-run average of a random variable over many, many trials. It's a weighted average of the possible values. This leads us to the formal definition and formula. The formula for the expected value is the sum, for all possible values of x, of the value x multiplied by its probability, p of x equals x. This formula calculates the weighted average we just talked about. Let's break that down. You take each possible outcome, multiply it by the probability that it happens, and then you add all those products together. Let's see how this works in practice. Let's apply the expected value formula to worked example 8.3. In this problem, we're given the probability distribution as a formula instead of a table. The random variable y can take the values 2, 3, or 4. Our task is to find its expected value. The first step is to use the formula to generate the probability distribution table. This will make the expected value calculation much clearer. First, let's calculate the probability when y equals 2. We plug 2 into the formula, 0.125 times the quantity 2 squared minus 7 times 2 plus 14. This simplifies to 0.125 times 4, which is 0.5. Next, for y equals 3, we plug in 3.125 times the quantity 9 minus 21 plus 14. This gives us 0.125 times 2, which is 0.25. And for y equals 4, we plug in 4.125 times the quantity 16 minus 28 plus 14. This also gives us 0.125 times 2, which is 0.25. Now we can put these values into our table. Here's our completed table. Notice that the probabilities were 0.5, 0.25, and 0.25 add up to 1, as they should. Now for step 2, calculate the expected value using our formula EY/PY equals y. We'll multiply each value of y by its corresponding probability and sum the results. So it's 2 times the probability of 2, plus 3 times the probability of 3, plus 4 times the probability of 4. Plugging in the numbers, we get 2 times 0.5, plus 3 times 0.25, plus 4 times 0.25. This equals 1 plus 0.75 plus 1, which gives us a final answer of 2.75. So the expected value of y is 2.75. One of the most common applications of expected value is in analyzing games of chance to determine if they are fair. Let's explore this idea. What does it mean for a game to be fair in a mathematical sense? In probability theory, we define a fair game as one where the expected gain for each player is 0. This means that, on average, over many times playing the game, you would expect to break even, not win or lose any money. Let's analyze a game in worked example 8.4. Here's the scenario. Hiroki pays $4 to play a game. He rolls a standard die, and his payout is the number he rolls. For example, if he rolls a 5, he gets $5 back. We need to determine if this game is fair. To do this, we need to calculate Hiroki's expected gain. The expected gain is his expected payout minus the cost to play. First, let's find his expected payout. The payout is determined by the roll of the die. So let's define our random variable x as the score on the die. The possible outcomes for x are 1, 2, 3, 4, 5, and 6. And since it's a fair die, each has a probability of 1/6. We calculate the expected value of x, which is the expected payout. Multiplying each outcome by its probability and summing them up, we get 3.5. We saw this exact calculation earlier. So on average, Hiroki can expect to receive a payout of $3.50 each time he plays. Now for the final step, compare the expected payout to the cost. Hiroki's expected gain is his expected payout of $3.50 minus the $4 he paid to play. This gives an expected gain of -50. So is the game fair? No, it is not. Since the expected gain is not zero, the game is not fair. In fact, it's biased in favor of Jenny. On average, for every game he plays, Hiroki can expect to lose 50 cents. To really master these concepts, practice is key. Let's work through a couple of problems from your exercises together. We'll start with question 13, which combines several of the skills we've learned. We're given this probability distribution table with an unknown k. We need to find k, then find the probability that x is greater than or equal to 3, and finally calculate the expected value of x. Part A, find k. Remember, the sum of probabilities must be 1. We add the known probabilities 0.2 plus 0.1 plus 0.3 equals 0.6. So 0.6 plus k must equal 1, which means k is 0.4. Part B, find the probability that x is greater than or equal to 3. This means x can be 3 or 4. We add the probabilities for x equal 3 and x 4. That's 0.3 plus our newly found k, which is 0.4. The result is 0.7. Part C, find the expected value ex. We use our formula, multiply each x value by its probability, and sum them up. That's 1 times 0.2 plus 2 times 0.1 plus 3 times 0.3 plus 4 times 0.4. Adding these products, 0.2, 0.2, 0.9, and 1.6, gives us an expected value of 2.9. Excellent. Let's try one more, a problem where we have to build the distribution from scratch. A bag has 8 red and 6 yellow sweets, so 14 total. We pick 2. X is the number of yellow sweets. We need to find its probability distribution and then its expected value. The number of yellow sweets x can be 0, 1, or 2. Let's find the probability for each. The probability of getting 0 yellow sweets means getting 2 red sweets. That's 8/14 times 7/13, which is 4/13. The probability of getting 2 yellow sweets is 6/14 times 5/13, which is 1591. For p of x equal 1, we can use the shortcut, 1 minus the other probabilities. This gives us 4891. Now we have the distribution. Let's find the expected value. We calculate ex, 0 times its probability, plus 1 times 4891, plus 2 times 1591. This gives us 4891 plus 3091, which is 7891. This fraction simplifies to 6/7. So on average, you would expect to draw about 6/7 of a yellow sweet. Let's wrap up and review what we've accomplished today. We started by defining what a discrete random variable is and how to represent its likelihoods using a probability distribution. We established the fundamental rule that all probabilities in a distribution must sum to 1. Then we introduced the crucial concept of expected value, E of x, as the long-run average of a random variable. Finally, we applied these ideas to analyze the fairness of games of chance. You now have the foundational tools to describe and analyze situations involving discrete random outcomes. Looking back at our objectives, we have learned about discrete random variables and their distributions. We can now find the expected value, and we've seen how to apply this to real-world contexts. We have successfully met our goals for today. In our upcoming lessons, we will build on this foundation to explore specific, very important types of probability distributions, such as the binomial distribution and the normal distribution. Thank you for your attention.